we're going to rewrite this equation as follows. 1/2 I omega squared, where we're going to give I, which by definition is the sum total, I equals 1 to n of m sub I, r sub I squared, a fancy name, moment of inertia, which is sort of the red bow in the white box. It's really ugly, but it's unfathomably useful. Now, even before we talk about the ugly thing for a second, we went from the translational space of 1/2 mv squared, which we're all pretty comfortable with, to the rotational space of 1/2 I omega squared. Forget about the ugly thing just for a second, we're going to come to it. And you can still see that pretty mapping between the black equations of translation, which I haven't drawn up there, and the red equations of the rotational space, because 1/2 mv squared has now morphed into 1/2 I omega squared. And we know omega is our rotational velocity, and so I sort of is kind of a rotational mass. Does everybody kind of feel that? So what I want to do now is focus a little bit more on this. And I'm going to give you a definition in words to write down. But this is one of the hardest concepts to ingest. And so I want to just talk to you even before you write stuff down. Remember back in chapter 5, we talked about the inertial properties of matter, or of mass specifically. And I made a couple of comments. You know, there's the chemistry view of mass, and there's the physics view, and they don't compete with each other. But in chemistry, we think about protons, neutrons, electrons, even positrons, right? Because we talked about antimatter a little bit. These things have mass. An electron's mass 10 to the negative 31st kilograms. But really, from the inertial standpoint, objects of mass have inertia. And the larger an object's mass, the more inertia it has, the more it's going to resist changes in velocity. Said another way, the more it's going to resist acceleration, right? Changes in velocity or acceleration. This moment of inertia thing is essentially the rotational equivalent of mass when we get into these considerations. Now, the mass is the mass in kilograms. The mass of this thing is some mass in kilograms. I can take this on a scale with me, figure out what it weighs, divide it by 9.8, and get its mass. Or 32, and get its mass in the British system. But this baby here is much more complicated than just a plain old kilogram thing. And so this is kind of what this means. This is a little conceptually grueling, but just stay with me. We have the kilogram part of the mass here. Because if you just consider the summation, that's the total mass of the object, right? I equals 1 to n of every single particle. That's the total mass. That's our plain old kilogram mass. But when it comes to rotational considerations, the distribution of the mass about the axis of rotation matters a lot. It doesn't just matter a lot. It matters a lot because this radius, this distance from the axis of rotation is squared. So the degree to which this object, this extended object, is going to resist changes in angular velocity, is going to resist angular acceleration, depends on its mass distribution about the axis. And there's an infinite number of axes we could pick here. So that mass distribution depends on whether you're spinning it about the y-axis like this, the y-axis over here, the x-axis over here in the middle, the z-axis out of the whiteboard. It's all going to change. And so we have a much more complicated situation. Now, all of that ugliness stated, let me give you a couple of words to put in your notes. And then we'll do an example. We'll actually calculate a moment of inertia for a discrete system of 4 objects, 4 points, very doable with the summation. And then we'll calculate some rotational kinetic energy.